So next, I'd like to introduce Darragh Costello. Darragh, if you want to get your slides up and ready there, and just to say, Darragh Costello is a fourth-year civil engineering student here in the University of Limerick, and we're going to hear about evaluating the impact of connected autonomous vehicle behaviours on traffic congestion. So, Darragh, in your own time, and when you're ready, take it away.
Thank you. Let's get started now. Perfect. So my name is Darragh Costello, and today I'm going to take you through my research into evaluating the impact of connected autonomous vehicles behaviours on traffic congestion. I suppose I understand a lot of you listening today will not have an in-depth knowledge of autonomous vehicles, so I'll start with something that we all know too much about: congestion. Congestion can actually form in many different ways, and it can form in recurring events such as rush hour traffic, which you most commonly see, or can occur in non-recurring events due to traffic incidents or work zones. For this study, I focused mainly on recurring events. Congestion has a lot of effects in our lives throughout the year. It is estimated that it takes 54 hours of our year on average spent in congestion. The emissions produced by congestion also add to the extreme amounts that are already produced by the vehicle fleet worldwide. Thankfully, there are some future solutions that are being researched, one of which is autonomous vehicles. Autonomous vehicles look to increase the capacity on our road networks by reducing the minimum gap between manually driven cars and also creating a more uniform pace throughout the network. Connected autonomous vehicles are similar, except they'll be able to communicate both to each other as well as to infrastructure. They'll be able to relay messages regarding congestion or even traffic incidents further up the network back to following cars. This will allow following cars to either reroute onto a different network or to slow their pace to allow traffic flows to return to normal. The hypothesis I've adopted for this study is the adoption of connected and autonomous vehicles over the coming 40 years will significantly reduce recurring traffic congestion. I've aimed to prove this by taking these 7 objectives, including undertaking detailed literature reviews, using microsimulation to model traffic flows, as well as implementing autonomous vehicle behaviours into microsimulation. First step was to undertake a detailed literature review to understand all the topics related to my study. Of course, first was the autonomous vehicles themselves. Currently, there is 5 levels of automation specified, of which level 3 can commonly be seen on roadways right now through vehicles such as the Tesla Model S. These vehicles will open up scenarios where platoons will be available. This will kind of segregate heavy goods vehicles that move typically slowly to one section of the road, allowing faster, smaller moving vehicles to avail of quicker speeds and reduce congestion themselves. Congestion can also form in many different ways. There is extended congestion patterns which are created by scenarios such as this graphic here on the right, where if one vehicle brakes harshly, this can then cause a knock-on effect through the system, causing propagation hundreds, even thousands of meters through the system. In order to model these traffic phenomena, I've used microsimulation. This is a tool that is commonly used by traffic engineers to analyze networks' capacity and efficiency. You can model adverse events such as traffic incidents or controversial techniques like cabs without causing disruption to a network. There are many different companies currently involved in research into autonomous vehicles such as Apple, Google, and Audi. Google's Waymo 1 has been operating a ride-sharing service in Phoenix and San Francisco successfully for years now. This is a level 4 vehicle operating on these roads. While there's a lot of people investigating the effects of autonomous vehicles, there's a lot of researchers looking into the adoption cycle of the vehicles as well, as this will have a huge part to play. I understand that a lot of people will have a lot of reluctancy in stepping into a vehicle that's completely out of their control due to safety and privacy factors. With all new technologies, there is obviously significant cost related to them too, and this will have another impact. For my model, I've used the diffusion of innovation model as my base, and along with other investigation into other research studies, I've been able to produce this model. I've selected key dates such as 2040, 2050, and 2060. which are used to replicate penetration rates of 30%, 60%, 95% calves. I've used PTV Vism in this study in order to model traffic flows. This is an analytical tool used by traffic engineers to analyze network capacity by looking at the interaction between vehicles. It is typically used for smaller, more intricate networks. However, the results can be put together to produce models for entire cities, if not counties. It uses equations to produce typical driving behaviors related to acceleration, desired minimum gap, and lane change control. In particular, this model uses psychophysical models, the Wiedemann 74 and 99 models. These also take into account the driver's perception of minimum gaps for lane changing maneuvers. Here we can see the parameters that are used in these models. In these snippets here, you can actually see how PTV Vism operates and shows the lane changing maneuvers and car following behaviors of vehicles. In total, there was 30 simulations run. I varied traffic flows to the main line as well as the merger lane. I also varied the percentage of heavy goods vehicles accounted for in these compositions. In order to get an understanding of the particular parameters, I also looked at different parameters specified by individual state bodies. The two that I looked at in particular were the parameters specified by the Wisconsin Department of Transport, as well as the German Highway Capacity Manual. The data gathered was then able to export it to Excel in order to produce graphical illustrations of it. I produced first these 2D speed time graphs, as you can see in the bottom left. These show average velocities for particular time steps in the simulation run. The 3D graphs you can see on the bottom right are actually made up of slices taken at particular points on the network. This 2D graph on the left is showing the merger point on the network. And from the 3D graphs, you can see how congestion can travel back the system and cause it to get worse. In actually implementing calves into the system, I looked at two particular parameter sets, the Atkins level 4 parameter set and the Zeidler set. Atkins level 4 was a lot more in depth and looked at the lane changing maneuvers and minimum gap specifications as well. When inputting these, I input them at 30, 60 and 95% as previously mentioned. In order to form comparisons, I first made a base model. I used the German HCM base as my base model, as this showed extreme congestion, as you can see here, and also significant propagation. When input at 30%, you can see minimal effects in terms of localized congestion at the merger point. However, the optimized car following parameters have shown extended congestion to be reduced significantly, as you can see in comparison between the 3D graphs here. I then looked to input it at 60%. Here we can see a significant reduction to the localized congestion, accounting for 50% total reduction. And most extending congestion patterns have been removed from the system, apart from certain slices here. Input at 95%, almost all extended traffic patterns have been removed from the simulation, and 82% of localized congestion has also been reduced. It must be kept in mind as well that this traffic model was run at extreme traffic conditions, so any improvements show serious improvement. So to conclude, I'd just like to say that the results show obvious benefits from the introduction of cabs onto networks. These improvements will have impacts on everyone's day-to-day lives. It will give us added time from the removal of congestion, as well as we will have more free time in the vehicle, as we will not be spending it driving. We'll be able to spend it either working or even spending time with family, friends on long car journeys. If I was to further my research, I would look to input this platoon behavior as previously mentioned, and as is commonly known that cargo is increasing on the roads, and seeing this behavior account for the HGVs would be interesting. I would also look at the effects that it would have on the load effects on long span structures such as bridges. Thank you all for listening, and I'd like to open the floor to any questions.
Just before we take any questions, and thanks very much, Darragh, I'm just going to stop the recording there, if that's all right.
Yep.